Right, so it looks like everyone's starting to warm up on that, so I'll give you more time to work through this. And then don't forget your papers, so right end of the quarter coming up. And for your rough draft, they only need to be 3 pages. So just kind of a reminder. So rough draft. So 3 pages, so don't forget about that. Try to get that in ASAP. Yeah. All right, I'll let you keep working.
And then that one was the negative. I trust your program. I trust my prediction. I didn't make it out front because I subtracted expenses.
So who wants to put this on the board for us? And we could break this up too, so we could start with, who wants to just put the R part of our rice on there? Anybody want to walk us through, or we? All right. Yeah, do you want to do it on the far board over there? There's like more space. And feel free to tag out if you want and voluntold a classmate or something. All right. Wait, can I pause you for a second? You're doing great. I just want to make sure. So does everybody understand how we got to here? And I just want to repeat for the online people. Right, we just set up our initial conditions, and then you notice with our two coefficients, that tells us how much more it's going to be adding versus this one is, of course, subtracting x. And then he set up the initial conditions, and then, of course, we know it's going, right, all the way to the product. Since we have no products, we don't have to do our Q or anything. And then we have minus x plus 2x, and solving for equilibrium. So that looks great. So does anyone have any questions up to this point right here? So K is just our equilibrium, and then I tried to post it. So we were still using the same KC from yesterday. So I can rewrite that. All right, so yeah, if you don't mind continuing, you can still continue going for it. I just wanted to pause and make sure we all understood how to get to this point. All right.
minus x equals 4x squared, and then we can subtract these values from this side, leaving us with 4x squared negative x 0.36 is positive, and we will take the addition point be 0.36 minus 0.001. And then we put this to the quadratic equation. We'll get two values, a positive and a negative value, and we'll probably will have a negative concentration, just because that results in a negative concentration of our value. So in this case, it would be negative NO2 if we would have a negative value. And the value that I got for x was 0.02, and then we have to take this back to this, and count out 0.0 equals 25, minus 0.02 equals our equilibrium concentration is 0.05, and then we have a 2 times substitution for x value gives us a 0.04. Equilibrium for equilibrium concentration is 2. I believe that is the extent of the question.
Yeah, that was excellent. You did a lot. What was the last value for
Oh, that was
N2O4?
N2O4 was 0.07.
Okay. 4.0005. I didn't round as much, but excellent. That was a beast. So you should give him a hand for that. So a lot of algebra. So we can kind of walk through it. So basically, right, you had to get to this point. So everyone follow. And then from here, it was just all algebra. So thank you, Alira, for showing all that. That was awesome. So I copied your work. And then, of course, if you don't have a fancy calculator, you can also plug this into your quadratic equation. Yeah?
How do you know which x is negative and which one's positive? That's the part I get confused, because I don't know which way it's to go, like which direction.
Well, because did you get two values for x, right?
Yeah.
So-
But I mean, like with the in the little table thing, you get the 2x and negative x. I had it flipped with the negative 2x and positive x. How do you know which one's negative?
Oh, like that this was.
Yeah.
So you have to think about which one is going to be decreasing. And so that depends on like what your starting concentration is. So in this case, because we had all reactant, we knew that the reactant has to decrease, right? And we can't just like make magical more reactant, which kind of helped us with the quadratic, right? Because then we'd get, like we can't have a negative making things, negative x, that doesn't make sense. And then if this is, you know, going away, then we're making 2 times as much product then.
So if it was NO2 changing into N2O4,
Yeah.
the x would be negative on the other side?
Yeah, so that was, so I scrolled back up, so that was Monday's, or Tuesday's, sorry, I can't keep track of the days. Tuesday's scenario, right? So Tuesday we started with all product, and so then we were saying, okay, well then it's going backwards. So yeah, just like you had said, the positive x then was on the reactants because we had 0, so we had to be adding, and then meanwhile the products were subtracting.
So whichever one you, like the value you're given, that's the x that's negative?
Usually, but except, what if you were given like a weird scenario where you had initial conditions and then you had to find Q, right? So sometimes we might have to find Q, so let's review with Q, right? So then that's where Q comes into play, is if it's not as clear, so we were given, right, all reactants or all products, so that was clear. But if we were just given like random starting amounts, then that's where we get our Q, get our snapshot, and then we have to say, okay, are we losing reactants, right, and making more products like over here? Or are we above the K and then we're going to be going in the reverse direction? And then that's where you know which one's negative X and which one's positive X or whatever. So I would have to look at your exam to see how tricky I made it. I don't remember at the moment. All right, any other questions on this one? This was good. All right, let's do some more practice. And it's now kind of same thing, except now with just our units of pressure. So it should feel just the same. So now, surprise, surprise, we're looking at a reaction of iodine and chlorine again and making that iota chloride. And so we have a Kp of 81.9 at 25 degrees Celsius. And we have a reaction mixture initially with these conditions, so 0.1 atm of iodine, 0.1 atm of chloride, and then 0.1 atm of iodo chloride. So find the equilibrium partial pressure. So this is just kind of what we were saying, right? So now we don't know which way it's going. So as a hint, right, we need to find our Q first to even figure out what way we're going. So I'll let you guys try that. So let's start going over it. So what did you find for Q? Which way is this going? I guess we should start off with our KP expression. And technically I shouldn't have used the brackets, but I always forget to use the little p's. So what do we get when we plug this in? So 0.1 squared over 0.1 times 0.1. So what do we get? 1. And so with this, so which direction is it going to be going? Which one's? So forward direction. So right, so we need to go forward. And so what does that mean for our x? Let me write it out first, the reaction. And so let me set up our initial conditions. So 0.1, 0.1, 0.1, and then, so what does that tell us? So which one is x or minus 2x? What are we doing here?
Since it's going forward, that means the reactants are going to be consumed to make the bonds, so the reactants should have negatives on them, and the product should have plus on it.
Plus and then 2x, right?
Yeah,
Or-
with the 2x because if there's 2x.
Perfect. So is this what everyone got from there? So excellent. And so now we can plug in our equilibrium, of course, solving for our change. And so now math time. Let's see, oh yeah, there's our KP. So now we can, of course, plug this into our equilibrium expression. And I'll just rewrite it. And then, so what do you notice about this? This is kind of nice how the math breaks down. So what can you do from here? How can we get rid of these?
You can put those two together, and you get 0.1 minus x squared, and you square both sides.
And then, so what do you do? Then it equals 81 point, oops. So then you can take the square root, right? So that's kind of nice. So 0.1. So then you're just left with this. And then let me pull up my calculator to get the square root. So 9.05. And so then just keep doing algebra, so then you can multiply and distribute. And then just get x on one side, numbers on the other. Oops, sorry, did that the wrong way. So do we get 0.0729 or so for X?
How did you get that extra 9.05?
So got to here, and then I multiplied everything by this 0.1 minus X. So then distribute this, right? So then you get 0.905. Minus the 9.05x, right? And then simplify the variables. So now plus, or add 9.05x, right? So then you get 11.05x, and then minus 0.1 gives you the 0.085. And so then now plug x back in to our equilibrium. And so luckily they're the same, so 0.1. So then we should get 0.027 ATM for iodine and chloride. And then, let's see, what do we get? And then do we get 0.25, or you could, yeah, 0.25 ATM for iodochloride? Questions about that one? All right, so then the last bit is when we can simplify the math. So obviously we are going to do this quadratic a lot. And this will probably be more helpful when we get to our like weak acid chapter as well. So keep this in mind. Because again, we're going to be seeing a lot of equilibrium. And there, again, we'll get a sense of our strength of our acids, but then we'll see a lot of the times we can use that 5% rule there. And so let's look at this. So when our equilibrium constant is very small, then the position of our equilibrium favors our reactants. And so that means that our change would be pretty small. And so then if it's less than 5%, we can make the assumption that it's close enough to our initial conditions. And so again, that's where our approximation comes into play. And so what we'll have to do is, if we think it's appropriate to make an assumption, we will do that. We'll solve for x, and then we'll double check that x, make sure that our approximation was indeed appropriate and that it was less than 5%. Otherwise, if you misguess, which does happen, and you're over, then you will have to kind of redo it and do the quadratic. And so let's practice. So this is, again, one of those scenarios. And usually I say you want to find like a 10 to the third at least difference, or 10 to the fourth. And once you see that large, like 10 to the third order of magnitude, that's usually a good indication that an approximation is appropriate. And so again, in this case, we have a 10 to the negative 7th equilibrium constant. So way past, right, this 10 to the third or fourth factor I tend to look for. And so now let's look at our scenario. So we have a 0.5 liter vessel, has 0.0125 moles of our hydrogen sulfide at 800 degrees Celsius. And then it seems to decompose into hydrogen and disulfide. And so find the equilibrium concentrations of H2 and S2. And so let's actually just walk through this together, since we're going to do an approximation. And so again, we're saying we're starting with only reactants. So we know what direction it's going in, so this will be minus 2x. And again, right, we see we have a pretty small equilibrium constant. there's our reaction. Oh. And then our initial conditions. So 0, 0. Like we said, the change, so minus x plus 2x and x there. And solve for equilibrium, so 0.0125 minus 2x, 2xx. And so then we can plug this in to our equation, so our Kc. And so that was equal to, so H2 squared times S2 over hydrogen sulfide squared. Let's pause there for a second. Let people catch up. So 1.67 times 10 to the negative 7th. I just haven't written it yet. I was just making sure, so everyone got to here. And then so we can start to see where this is going to get nasty. And so we start plugging this in, so 2x squared times x over 0.0125 minus 2x squared is equal to that equilibrium constant. And so let's continue to simplify this a little bit more so that we can square this, right? So that's 4x squared times x, and now we're 4x to the third. And we'll just leave this still as this 0.0125 minus 2x squared equals our Kc. And so now we're at this point, right? So now we have a cubed equation, so that makes it obviously more difficult to solve. And so this is where we can try to use our approximation. So use our 5% approximation at this point. And again, that's because we're comparing, right, our initial concentration. We're saying this is small, so this minus 2x doesn't matter. And that will help our math a lot. And so now we have 4x cubed over, and let's get a number. So 0.0125 squared. Is that right? I'm just making sure I plugged in the right number. All right, so now we get 1.56 times 10 to the negative fourth equals our 1.67 times 10 to the negative 7th. And so now let's just algebra, get rid of this. And you guys can let me know what you get as well. And then divide it by 4. So I got this, but make sure that I plugged everything in correctly. Watching the chat too in case y'all are following.
Yeah, I got that too.
So x equals, we're saying 1.86, or I guess I'll round that, 1.87 times 10 to the negative fourth. And so let's go ahead and check our approximation, right? Because we don't want to plug in for x and solve our values. It's not appropriate, so let's look. Oops. And so all we do is we take this value of X divided by, right, this initial concentration, what we had said was irrelevant. So let's check that out. So times 100 to make it a percentage. So yes, right, it was only 1%. So we were okay to make that assumption. Let me write that out. So divided by, and so now we can find our initial concentration, or sorry, our equilibrium concentrations. So where's my X? I already forgot what X was. So for our hydrogen sulfide, I have this value, 0.0121. And let's see, so H2. And let's see, so this would be our S value, right? So S2 is just X, so 1.87. And then H2 should have been 3.74 times 10 to the negative fourth. So pretty small. And right, that makes sense. So you can always just kind of think about that, quick sanity check, like, yeah, that was a pretty small equilibrium constant, so it moved a pretty small amount to the right. And then, of course, we could also double check ourselves if we wanted to re-plug back in to KC. And so we could just make sure that that all works out. So that squared times our 1.87. And then divided by our final concentration. Oops, did I plug something in wrong? Oh, I didn't square the bottom. There we go. So that matches roughly with our equilibrium constant. Questions about this one? Feeling okay? All right, so the last bit is just going over Le Chatelier's principle, but I think lab will give you a really good sense of this. So all this is saying is basically, right, how can we disturb our equilibrium, and then what happens. And so a lot of this is kind of wordy. So let's kind of, I think the graphs are better. And let's look at this scenario for a second. And so you notice, right, you kind of stress the system, and then it's going to try to fix it. So let's kind of look at, of course, our usual dimerization scenario. So now we have N2O4, and again, it disassociates to make two equivalents of NO2. And so obviously this was a closed system, and then part of Le Chatelier's principle is, well, we open it. And again, you're going to do that in lab in part C. So if you already did lab, you can think about how you stress the system. If you haven't, right, this is what you're going to be doing. And so in this case, they added more of our product. But if it was at equilibrium, well, now it's disturbed. And so that's what you're going to see, right? You had your equilibrium, you disturbed it, so now you add more NO2, and so that's going to drive then the dimerization. And let's look at the graph, because I think these graphs are nice. And so here's the scenario that we were talking about. So again, at equilibrium, so reaction still going forward and backwards, and then we artificially disturb our equilibrium. And so, of course, spiking, in this case, it's represented as our products. And then, of course, right, we see the product decreasing as then the reverse rate is favored. So then we're making more N2O4. And, of course, we see that dimerization happening, and then new equilibrium established. And so that's basically what this says, except kind of more convoluted. And so the words don't quite match the pictures, but again, kind of same thing. So we can do this adding reactants and imagine how it would change our equilibrium. And then the caveat in the text is it reminds us, right, that as long as it's not something that was a solid or a liquid, again, thinking like that neat reaction, or if you have H2O liquid as part of your reaction, right, those concentrations wouldn't change, but anything else that you're stressing and adding the system with, well, that would affect it. And so let's think about our lab, actually. So we had iron 3 plus our thiocyanate, gave us that dark red complex. And so, again, you'll see this. So we can think about it. So if you add your reactants, so if you add any sort of, and you saw that in lab, it could have been any iron 3 source, so that's why they wrote it so funny. So it could be, right, iron 3 nitrate, iron 3 chloride, doesn't matter. If we add any of those into our system, we're adding reactants, and then that's going to increase, right, our forward rate of reaction. And then you'll see that in lab, hopefully by it, turning nice and dark red compared to your equilibrium standard. And then again, lots of words just to kind of say all that. So again, it's saying, right, it initially increases the rate of the forward reaction just because we've added more products. And then it again proceeds to the right until equilibrium is restored. And then, of course, reverse reaction is not affected until you start, of course, adding more products, but still goes to equilibrium. And then obviously, right, K, not affected. So that's always helps us. And obviously how we've been solving everything is K is always the same. And so same thing. I'm blanking on a good. Oh yeah, don't you add, because if you add trying to remember your lab reaction. Let's think of another one before I screw it up. So you can also do, so copper plus hydroxide gives you this cloudy copper hydroxide solution once they're complex. And so this is easy then to think about. So if we have our, again, copper plus hydroxide ions, and then at some point, right, they make this solid compound, well, we can remove reactants. So let's say we were to add hydrochloric acid to this system. So then they react, right? So then we've removed hydroxide, and then that's going to cause our equilibrium to favor then our reactants since they removed them. And then it would become clearer from, again, right, more of our copper hydroxide dissociating to make liberated hydroxide ions, and that would be clear.
I think we added hydrochloric acid as well, and that's what made it lighter, is that the reaction that you're describing?
Yeah, I wanted to say there was a similar effect, but I didn't want to speak without having done it yesterday. So yeah, you should see the same effect with this one as well. So they're probably making an iron chloride complex, and then that would be removing iron from the solution. And so again, right, a lot of words just to tell us all that. So again, right, it has to be something that affects our equilibrium concentration. And then we have removing our reactant decreases our forward reaction rate. So relatively speaking, right, the reverse reaction is going faster. And then again, equilibrium is restored. And then blah, blah, blah. This is just words to say what happened. And always K is constant. And so again, we can look in these graphs that kind of help us, although the graphs didn't show any removing, which is a little irritating, but whatever. And so this one, again, now we're adding reactants, so artificially spiked. And then we see how the product is made, so trying to shift away from that stress of too much N2O4, and then new equilibrium reestablished. All right, so let's look at this one. So take a look at this scenario, and then what happens if you add CO2? Will that cause a shift? And what happens if you add calcium carbonate? So what would CO2 do? Which way would it shift? So left, right? So it would then favor our formation of reactants. So too much, so we have to get back to equilibrium. What happens if we add calcium carbonate? Check out the, so then what, no effect? So no effect for our calcium carbonate though, since it's just a solid pile, so it doesn't have a concentration. Let's see in the chat. And so let's look at the last bit of this. And so then we said, well, what happens if we add a gas to a gas phase reaction? And so of course if we add a reactant, right, that will cause the equilibrium to shift appropriately. But then what happens if we add an inert gas? And so adding an inert gas, though, has no effect since it's not interacting, right? It's not reacting, and it does not affect our partial pressures. And then, of course, volume, though, can change the equilibrium for gases. So decreasing the volume of the container, right, increases the concentration of the gases and increases our partial pressures. And then just a reminder, right, this would not apply to solutions. So, right, they're not compressible like gases are. And then if our partial pressure of gases increase, then our total pressure increases. And then, so what's kind of cool about this is the equilibrium shifts to remove the pressure, and it does that by shifting to the side with fewer gas molecules. So that could be a way to kind of get a reaction to be favored, is doing something at high pressures, and that will help produce less molecules of gas. And so again, equilibrium, so if we change our volume, changes the pressure. And K is never affected though. Only by temperature, but again, wouldn't be comparing that. So blah, so here is the nice graphical representation of this. And of course, why wouldn't we talk about the Haber-Bosch process? And so there's a reason why this occurs at high pressures. And so again, we talk about it a lot in this class, but as we keep diving into it, we kind of see why. And so very energy intensive reaction occurring at high temperatures and high pressures. And so now we see the high pressure part that answers that part of the chemical industrial engineering part of this. And so if our desired product is our ammonia. And so notice, right, we're reacting 4 moles of gas and making 2. So in order to help drive this very difficult reaction, they, again, run it at high pressures. So running at high pressures then, or decreasing our volume, would then cause it to shift to the right, again, favoring those less particles. And then, of course, right, decreasing the pressure or increasing our volume, that would cause it to shift back and favor our reactants. And so again, this would all go into whatever engineering conditions they've come up with, so trying to get just the right pressures and temperatures to get that reaction to go. All right, let's try this last bit. So what happens if we decrease the volume of this mixture, increase the volume, or add an inert gas? So take a minute or so for that. So what do we get for decreased volume? Right, you had it right. So left, so let's just write this out, right? So this has 0 gas versus 3 moles of gas. So now we can clearly see. And so chat is also in here as well. So yes, so we have decrease for going left, and then so increasing our volume. So what would that do? So yes, so that shifts it right. So less pressure favoring our gas formation, and then inert gas. So no effect. And then so what you also found out from lab is that basically we can treat heat like either a reactant or a product. So in this case, if we have an exothermic reaction, and so you guys can tell me later or in your post-lab write-ups whether you thought that formation of our iron thiocyanate, whether that was endothermic or exothermic. And so if you have an exothermic reaction, if you heat it up, right, so heat is acting as a product, so then it's actually going to shift away then, right? So then your exothermic reaction should shift left in the heat. So I don't want to give it away, so I won't say what happens. And then so for an endothermic reaction, heat would be a reactant. So if you were heating up an endothermic reaction, then that should occur more quickly and again favor those products. And then of course, right, adding heat does affect the value of K. And so this is just our summary. So again, exothermic heat is a product, and you can write it as such with that's the little heat symbol, this triangle. Or endothermic heat is a reactant. And so you can ask me about this if you've been in lab, and then we can talk about what you saw and whether your reaction was exo or endothermic.
Do we go into seeing how temperature affects the constant of equilibrium, or do we just say it affects it?
I think we just say it affects it. I don't remember. I'm sure there's some equation somewhere that, yeah, because I think that's for activation, but I'm sure there's some form with like constants as well, or I'm not sure, but I don't think we dive too into it. We usually just don't look at different temperature conditions. All right, so real quick before I let you take the quiz, so we have an endothermic reaction here. So our calcium carbonate disassociating. So what happens if we increase the temperature or decrease the temperature? Maybe think about where to add heat as a product in this reaction. And then this reaction is exothermic. So what will happen if we increase and decrease it? So what do we think? So we have our endothermic reaction. I'm just going to go ahead and write heat in there. So heat is basically a reactant. So what happens if we increase the temperature, left or right? So it goes right since we're adding reactants basically. So then that's going to shift it towards the products. And so then of course if we decrease it, now it's going to go left. And then so for our exothermic reaction, should be the opposite. So I'll write our heat now as a product. So what happens when we increase the temperature? So left or reverse. And then if we decrease the temperature, then that favors it. So we're removing products. So then it wants to go right. All right, I think we have gotten through chapter 19. So again, the equilibrium will keep haunting us next week. So we'll do more 5% approximations, just probably with acids and bases as the flavor. So keep practicing this. And then I'll go ahead and hand out your quiz. But then if you want to take a break, of course, take your break. And then email me if you want me to email you a quiz. So we have a whole chapter to cover next week. And then we'll do a review on week 11 on that Tuesday. Yes, we still have week 11. And then we'll exam week. So we'll meet up Tuesday for a review. And then Thursday we'll take the test.
Better not.
We always have 11-week terms though, because every quarter is 10 weeks plus exam week, so it's really 11-week quarters. Yeah, I forgot what the explanation was for why we went from 2 weeks of spring break to 1 week, though.
We're trying to line up with the other universities
Uh,
and stuff, and also they're trying to put more breaks in between spring and summer, and then summer and fall. I'm like, I don't necessarily want that.
I find it funny that the spring break is gonna be 1 week and the winter break was like an entire month.
Yeah, and next year, the next one's gonna still be 3 weeks. The next like winter break is still gonna be 3 weeks, and there's like 3 weeks in between spring and summer, and 3 weeks in between summer and